So welcome back to my recurring nightmare of having to record my own voice in a lecture. This being the continuation of hash tables. And before I talk about a more elegant and efficient way of resolving collisions, I would like to go to something that is a more basic premise in Java, and that is an object. That when a coder creates some new kind of object, and we'll say a cat, it automatically is a subclass of the object, that is capital O object. You don't have to state it. That is, you would never have to say public class cat extends object. The extends object is automatic. So every object that is created automatically inherits things from capital O object. These methods that you've seen over and over and over now, the toString method, the dot equals method for comparing the equality of two instances of our objects, and then this new one, hashcode. Every object that exists in Java has these three methods. It's oftentimes the goal of the coder to override any of these methods to make them more meaningful, to make them more logical for the object we defined. So if we were to have created this cat object, we might override the toString method to have our own version that might send out a string that has the cat's name and its breed and its weight. With the dot equals method, we'd first have to consider what does it mean for two objects to have equality, two different instances of the same class. What does it mean for them to be equal? Are they equal if they have the same name? Are they equal if they have this, if they're of the same breed? Are they equal if they're the same breed and the same weight? That's something that we would have to figure out. And then the hashcode method, a method that for an instance of that object will return some integer value that we could then shape into being an index. So we could store our objects in a place that'll make them easy to find. And that's all going to depend very heavily on the very particular database that we're building of these instances of objects. So we'll consider some new type of object called a widget. It'll be a very simple one. It'll only have a name as a data field just for simplicity's sake, so we're not covering up the screen with just a wall of text for code. So the name being the only data field is also going to be the search field. So imagine that we've already got a bunch of instances of widgets stored in a hash table, and the client then wants to search for a particular widget. So they'll type in the name of the widget they're looking for, and the search will report back whether or not they found it. So since the name for widget is likely going to be a string, the string object, being something that's been well established in Java for decades, is already got a hashcode method. It's got one that's really good. The strings hashcode gives us numbers that are across a very wide range of numbers. But just for the sake of showing you this overriding of the hashcode method, we'll make our own. It won't be nearly as good as the one that's already built into the string object, but it'll use some of the same ideas. So it's important to note that these hashcode methods are not going to be modding these numbers by the size of the array. That consider that for public class widget, that describes the DNA for what it means to be a widget. It doesn't know whether we're going to need to have a database that'll store 100 instances of widgets or a quintillion. It has no clue. Just as my DNA doesn't know how many students I have in my classes. So it's going to be the responsibility of the client program, the program that's going to take care of reading things in from the database and allowing whoever is running the program to search for something. It's going to be the responsibility of that program to do the modding of the hash code by the size of the array. It's going to know how many elements need to be stored. So here is this very simple widget object. So you can see it has the single data field, the name, and it's got a constructor, a single argument constructor, and it's got the toString that we've now have it overriding the one that's automatically inherited. It's got the dot equals method that's overriding the one that it inherits from object. These are sort of standard things to do when you create an object, is to make a constructor, override the toString. If you need to compare equality at any time with instances of your objects to override dot equals. Again, consider that if we have a more complex object with many, many data fields, we'd consider what are we testing for with regards to equality? Which data fields do we really want to look at? And then here is sort of my low rent version of deriving a hash code. That is taking the search field, which is the name, and turning it into an integer. Again, the one that's already built into the string is much, much better. It would be less typing and more effective if for this method hash code I were to just return name.hashcode, name being the instance of the string, and just returning the hash code for that string. So that is something that I would do if I were coding this myself, but just for the sake of showing you the process of taking a complex object like a string and turning it into a number, I just have this integer that's going to keep track of the sum of all of the ASCII values of every character within the string, and then modified by multiplying it by the index of where it's placed, so that if you have two different names that have the same characters but out of sequence, they're not going to return the same number. It's sort of a low rent way of getting these hash codes more spread out. So the string ABC won't have the exact same hash code as BCA or CAB, all the permutations of how those can be arranged. So, so I have this sum that starts at 0. I go through and traverse to every index of every character of that string. I'll go ahead and I'll grab that character. So again, the char@at method returns a character at a certain index from a name. It's sort of as if name were an array. Consider that strings really internally are arrays of characters, and we're just going to go to index I. So when I starts at 0, name.char@, index I will be the first character of that string. And then I cast it into an integer, which gives me the ASCII value. Every character has its own unique integer that is associated with it. An uppercase A happens to have the ASCII value 65. An uppercase B has 66. An uppercase C has 67. You don't have to know those numbers, but you should know that A is 1 less than B and B is 1 less than C. And in order to get some separation between two different strings that might have the same characters but out of sequence, I just multiply that integer by the index of where it exists within the string, and I add it into the sum, and then return the sum at the end. So there is, a very simple version of hash code. This one has a lot of weaknesses in that if I were to be storing widgets that only have 3-character names, the names will be exactly 3 characters. And we'll say that, for argument's sake, that they're all uppercase characters. I'm going to end up with a pretty limited range of integers of all possible strings that I could be storing from widgets. Just consider those sums going from capital AAA all the way to capital ZZZ. If I needed to store, we'll say 1 million widgets, then I'm only going to be occupying a pretty small band of that array. So again, this is just to show you the process of overriding hash code. The one that already exists for the string is far superior. Worth noting that the one that exists for the string can return a negative value. So usually when people invoke the strings version of hash code, one of the first things they do is they get the absolute value of it. And then in the client program that does the job of either filling up the hash table or allowing somebody to search through a hash table that's already filled, that's going to have the responsibility of modding that number by the size of the array. So here is now building a simple hash table. We'll make an array of widgets, just a classic Java array, and we'll say that we're storing 100 of these. We'll go ahead and create a new instance of a widget, and this widget's going to have the name Marvis, maybe named after Marvis Frazier, the journeyman boxer from the 1980s. And we'll go ahead and grab its hash code. And now this is in the client program, so this now has the responsibility of modding that by the size of the array to get a valid index from the hash code, and I'll call that index, and it's the array at this index. This is where I'm going to be storing my widget. So if I can guarantee that there are no collisions after reading in all 100 widgets, then I could also be guaranteed that I'll have a constant time search. Every element that I store into array is going to go to its own unique spot. And when the client goes to search for something, they'll type in that search field. The program will derive its hash code. It'll modify the size of the array, look at that index, and that's exactly where it'll be found. So that is the efficiency that is possible in this perfect universe in which we don't have any collisions. But we can't always guarantee that. So again, the fewer collisions we have, we're going to get pretty close to constant time for searching. And again, this is a big deal, that if it only takes nanoseconds to search in a small array of widgets, then with constant time, again, very few collisions, we're going to get almost that same amount of work and resulting in the same amount of time for searching in a massive array of widgets. But the more collisions we have, that can get us closer to an efficiency that's much less attractive, linear time. Linear time isn't a problem if your array is of size 100, but if it's of size a billion or a trillion or a quintillion, linear time is pretty terrible. So I've already addressed, I'd say, the most simple code means of resolving collisions with linear probing, but we do want to explore other ways of resolving them, and ways where the fault of linear probing, the more collisions you have, the more likely it is you'll have more collisions. Ways of buffering that, of making it so that each new collision doesn't necessarily make it likely, more likely that we'll have more collisions. So a solution is, rather than just using a standard simple Java array as our hash table, is to use an array of containers, an array of arrays, or an array of lists of some kind. And here is a pretty easy way of making something better than standard linear probing with a single array of one dimension. Use a 2D array. Consider that every column is like a bucket. And once we get an element that we need to store into our hash table, we get its hash code, and that gives us the index of which bucket we're going to drop that element into. So storing a 94 goes into the column 4 bucket. 94 mod 10 gives us a remainder of 4. If we want to store a 37, we drop 37 into the 7 bucket. Right? 37 mod 10 is 7. We want to store a 60, we drop that into the 60 bucket. We want to store a 17, we drop that into the 17 bucket. There's place for it to go. And with this being a collision, since it's contained inside of its own container, it's not going to make it more likely yet, at least at this point, that we'll have more collisions like we would with a standard one-dimensional array. We want to store a 97. 97 mod 10 is 7. We drop that into the 7 bucket. Again, there's a place for it to go. So there's the concept behind bucketing. This also shares some of the same weaknesses as linear probing with an array of one dimension. The buckets might fill up. That would be unfortunate. If we wanted to store a 57, that's going to try to go into the 7 bucket, and it's now already filled. What do we do now? Well, we could linear probe over into the next bucket. What we've really done is we've created sort of a bit of buffer space for every single possible hash index. In this case, it's a buffer space of size 3. But if that gets exceeded, now we've got to probe over, and now it's going to make it more likely that there's the potential of these things bunching up, and one collision could make it more likely there's another collision. So we're sort of falling into the same weaknesses that we had with linear probing with an array of one dimension. But it's a little better at the expense of using some more memory. So there is another fault of this. The deeper the buckets are, the more buffer space we essentially have to store elements where they're colliding, the more memory we're taking. but what if we end up with very few collisions? Now we've got all this buffer space that is unused. So we've got the 2D array, which is a nice simple construct to code, but there's this issue where we have to have the overhead in memory to be able to go with this strategy. So with regards to our best case, no collisions, constant time is guaranteed. That's great. The worst case, if I were to have the worst hash code ever, I'd say the worst hash code ever would just be return 0. It doesn't matter what the search field is, it's going to try to put everything at index 0. Well, now we've got the same worst case as linear probing with a standard one-dimensional array. It's going to be a linear search time. We'll be doing a linear amount of work. It's no better than just searching through an array that is just completely randomly arranged. So, but still, we've got something that's the potential for being better. But what's better than better? What could be better than bucketing? Well, it would be nice if these buckets didn't have to have a set size. So you can consider a hash table of lists, maybe an array list, maybe a linked list. These are containers that grow as they need space. They trim up the memory as you remove elements. Difference being that the array list has its own internal buffer space to give us a little better performance and speed at the expense of some memory. Now, the linked list is a much more one-for-one memory efficiency. So a linked list that stores 308 items only uses as much memory as it takes to store 308 items. But that can come at the expense of speed, depending on what it is we're trying to do. But the nice thing about these is that they're much more memory tight. We don't have to worry about these things filling up unless we exceed the amount of RAM that Java has allocated for us for storing things in a container. And if that happens, we have much bigger problems. But just make an array of lists. I'd recommend the linked list because of its memory efficiency. It's more one-to-one memory efficiency. So we want to store 94. This is called chaining because adding each new element in, it's like we're putting a new link on a chain. We don't have to worry about a bucket that fills up. 94 goes into index 4. It's the first link in that chain. We want to store a 37. It becomes the first link in the 7 chain. We want to store a 60. It becomes the first link in a 0 chain. We want to store a 17. It now becomes the second link in the 7 chain, the chain that is at index 7. We want to store a 97. It becomes the third link in that chain. And with these being lists, we don't have to worry about these things filling up. There won't be any linear probing necessary at all. So this is an improvement, in my opinion. So there's our advantages. These chains can't fill up like buckets, and we won't be wasting memory. Worth noting that if you go to use a list and you default to array list because of the first one that you were taught, the array list does use extra memory because of its own internal buffer space, where the linked list does not. We do have the same best case situation. If we have no collisions, then we're guaranteed our constant search time. Our worst case, though, if we had the worst hash code ever and they all tried to collide into chain 0, again, we have something that's no better than a linear search for an unsorted array. So again, some big improvements going from linear probing with a one-dimensional array to bucketing with 2 dimensions and now chaining with lists. But is there something better than this? And I think yes, we could improve on that worst case situation by chaining binary search trees. So remember, binary search trees, these are dynamic size containers, one-for-one memory efficiency, but they're always sorted, which means that searching within a binary search tree gives us logarithmic time. And logarithmic time is a lot better than sort of our classic linear time. So as we add elements, each one goes into its own binary search tree. And those themselves, if everything were to just go into one binary search tree, we would still have relatively good performance. So, so out of these different potential means of solving collisions, of resolving them, I would say that this would be the strongest out of all possible hash codes. Again, each one of these strategies could be totally appropriate for certain databases. But with chaining binary search trees, again, we have the advantage of we don't have to worry about these trees filling up. If they do fill up, we've got bigger problems. We're not wasting memory because they have this one-for-one memory efficiency. They don't have their own internal buffer space. And we get a much faster search time. Same best case situation, no collisions, no problems, constant time search. The worst case, though, is much better. If every single element collides into the same hash code, we now go to a logarithmic search time, which is still pretty fast. So consider with that logarithmic search time that if we've got a lot of elements, if we've got a billion elements, it's our worst case situation, all elements collide into the exact same chain. And then we're going to go to the worst case of the worst case. Worst case is we might be searching for the item that is at the lowest possible level of that chain, the lowest level of that binary search tree. Well, logarithmic time, it's going to be no more work than searching in 30 places, no more work than just searching in a standard array of size 30. Binary search tree being logarithmic efficiency, you can keep doubling the size of the tree and we only have to search in one extra level to find something. We go to something much bigger than that, and we're still doing a reasonable amount of work to search for something. So again, these are the worst cases of the worst cases. So we get to our tree of size billion or trillion or quadrillion or quintillion, and we'll still be able to search in that, if not in nanoseconds, then in milliseconds. And there is where we have something that's so close to constant time that we'll just consider it constant time. If you want to get really specific with chaining with binary search trees, you could say, okay, worst case, it's logarithmic time. What's the likelihood we're going to get the worst case of the worst case? If that happens, again, we've got bigger problems. But even with that, it's going to be hard to measure the difference in the amount of time it takes to search in a hash table of size 10 as it would size 10 quintillion. The background processes that are going on through the operating system are going to cloud our ability to measure the difference between those two. So there it is. Much better ways of resolving collisions.